abituando con la versione aggiornata.
Sì, lasciamene una copia anche lì. Let's wait still for 10 few minutes and then we start. Fortunately, the first intervention is recorded, and then now it will follow with this presentation.
Allow me to show because I need to change the program. I will not share now.
And then we will
But I
forward
need
to
permission. If you can give
Manuel Bowman.
in my Mac, I have to do later. Yes, after the
we
video,
will
because
have,
now I'm sharing.
Actually, a presentation which is most unique. That at the time of Rimateau time, I'm curious to hear, but apparently an instrument was sent to Xu-Guangqi to look at something. And I don't know if he did or not, but we will have a contribution on that today by Sigismondi. And how it is going, Tagi, you made any progress?
Yeah, I'm just working on that.
We have to discuss with you. I discussed with good morning. I discussed the problem of the creation of jets yesterday with Felix, and I think he was positively interested. He was going to look into that matter, and this matter will be very important to explain to you what and we have something to finish with Navik. And actually was important. Okay. I think we can start. And I will be the chairman today. And and proceed. Okay, there is a preparation of by Andrea Possenti. Andrea is the head of the radio group in Sardinia, and of course is part of all the collaboration and in the radio at European level, and let's see what he said.
morning, you all. I'm really sorry not being there to present this contribution in presence, and being also located in a part-time zone, unfortunately, prevents me to discuss directly with you the content of this presentation. In case questions will arisen, please let me know via the organizers, and I'll try to answer offline as soon as possible. What I want to give you today is a feeling about the growing role of computing radio astronomy, in turn leading to the opening of unprecedented needs and possibilities for innovation in a planetary scenario. Indeed, all our colleagues knows since a while that computing is part of everyday life. In doing both data analysis and simulations, and also in controlling and monitoring instruments and experiments. Nevertheless, it's important to remark that among all scientific disciplines, radio astronomy is probably the most demanding in terms of computing and data storage, at least among astrophysics, and probably also in general. In fact, which are the successful ingredients for doing a good radio astronomical experiment? First of all, you need to have a large radio telescope, as large as possible. The largest in the world at the moment, in terms of single dish, is the FAST radio telescope in China. Secondly, you need to have possibly a large field of view, which is very important in particular for investigating the radio transient, which became very popular and very important in science in recent years. Thirdly, you need to have a large bandwidth receiver to be able to collect as much as possible the information coming from your sources. But on top of all of this, you need very large computational power and data storage capabilities. In fact, the size of the data set with which we are dealing with in radio astronomy in the recent years go well beyond several hundred gigabytes, reaching easily terabytes, which implies the need of having the storage to store that, and also capabilities for reading that and analyzing that. This is even more true for the case of simulation, in which you want to start from general principle with an early universe version, and then develop that to see if the parameters set at the beginning reproduce or not what we are seeing now. That requires a huge memory in your computers and employ millions and millions of core hours for completing some of these simulations. You really need weeks or months with the largest computing facilities in the world. Another field where computing capabilities is very important is that of searching for very compact objects orbiting in a very tight orbit. This was, for instance, the case 20 years ago of the so-called double pulsar, which is still the best benchmark for testing general relativity effects. But we aim to have something more, to find as soon as possible a pulsar orbiting a black hole, and that imposes the need of analyzing the time series collected by your telescope with a very, very large computing power. If we will be able to do that, indeed, the reward will be great. Discovering a pulsar orbiting a stellar mass black hole will imply the possibility of measuring the mass of the black hole with a precision of 0.1% and its spin with a precision of better than 1%, thus, for instance, leading to test the cosmic censorship conjecture, stating that there are no net singularities in the universe. If we will be able to discover a pulsar orbiting a supermassive black hole, for instance, the case of a Sagittarius A star, we will be able to determine the mass of the black hole with better than 0.001% and even measure the quadrupole moment with a precision around 1%, which may lead to a direct test of the no-error theorem. So, we are already facing very large computing requirements for doing modern radio astronomy, but behind the corner there is a huge step upward in this field, namely that imposed by the implementation of the so-called SCA project, which involves several countries all around the world and was set up officially on March 2019 with an intergovernmental organization at which participated at the beginning 5 countries, among them Italy and China. And in brief, SCAO is telescopes with 2 sites, one in South Africa composed of many dishes distributed across several tens of kilometers and operating at frequency from 350 to 1500, 350 megahertz to 15 gigahertz. And the second one in Western Australia, composed by 100,000 of Christmas tree antennas and distributed again across several tens of kilometers and operating in the frequency interval between 50 and 350 megahertz. And the computing challenges to be faced by this system are really huge. We need to have a signal transport capabilities of order of petabyte per second, and computing at the level of hundreds of petaflops on site, and data storage at the level of exabyte capacity. But what is even more interesting in the context of what I'm saying is that this radio telescope will be improved more and more with the improvement of its computing capabilities. So in the next years, when the telescope will be finally set up, simply improving the computational capabilities will lead to a great improvement of the performance of the telescope itself. And that will not be the case only for the 2 sites at which the telescope will be installed, as is being installed this month, South Africa and Western Australia sites, but also all over the world. In fact, the signal from the antennas will flow to a central signal processor on site, will be moved not very far, but not very close to the site with the so-called science data processors, one in South Africa and one in Western Australia. And then from there, the data will be transferred to the so-called SCA Regional Center, SRC, the acronym, a series of data centers spread across the globe, which will have to deal with a data flow of about 320 petabytes of data per year. And the data set, each of them will be typically of order tens or sometimes hundreds of terabytes. Of course, all of that is being planned and is possible thanks to the development and the capabilities made available by improvement in computing, data storing and archiving, machine learning and artificial intelligence. In particular, machine learning is already very important in radio astronomy, and it will become even more important in the SCA era in activities likewise visualization of the data set, classification of the sources. When you have billions of sources, you cannot do that by hand. Identification of anomalies in a time series or in an image gain, you cannot do that when you have images containing millions of sources, and inference from what you see to underlying science. So we are all working in this, and this plot clearly shows how machine learning in astrophysics is becoming a key factor with more than exponential growth in the last years. As far as the hardware side, the Italian National Astrophysical Institute, INAP, is planning to have by next year owned SCA Regional Center at the so-called Technopole in Bologna. You can see the status of the Technopole construction at the moment. Indeed, a bit more advanced than in what appears in this picture. And it already hosts, for instance, the European Weather Center, ECMWF, and the Leonardo supercomputer, one still of the 10 largest supercomputers in the world. And in one of these buildings, there will be also the facility of INAP, which will comprise capabilities of order 1.52 petaflops and more than 10 petabytes, being an important asset both for astrophysical calculations in INAP and, first of all, for the Italian node of the SCA Regional Center. A node which Chinese has already set up some years ago. You can see here the picture of this hardware, which was the initial kernel of the Chinese SRC node. And of course, it is not only a matter of setting up hardware. You need to develop skills, to develop knowledge, and to collaborate a lot to optimize the usage of all these devices. And in particular, it's my pleasure, since the context of this meeting, to highlight that the Italian and Chinese involvement in these activities is very large, and not only because Italy and China, as I already mentioned, are two of the 5 initial partners of the intergovernmental organization leading to the construction of SCA, but also because Italy and China are two of the initial hosting countries for the SCA regional centers, and of course dialoguing and discussing and improving each other nodes is something which we are looking at in these months, and which will be really very beneficial for innovation on both sides. So I just wanted to let you know about this. Thanks again. I'm sorry for not being able to promptly answer your question, but again, you can deliver these questions, if any, to the organizers, and I'll be very happy to answer via email or other channels as soon as possible. Thanks again, you all, for your attention.
Thank you. And Billy, it's okay, everything correct? It was mainly with this presentation and to call attention on the bilateral, multilateral, and especially also the bilateral cooperation. Okay, and we can proceed now to the next lecture by Marek. Please.
You can share. Yes.
Il microfono lo tengo io o lo...
No, il microfono serve per
Sì.
qua. Oh, I need to.
Oh, Manuel is online, therefore be ready around 10:15 will be your turn. And I see that Fatemi is online, and the Olga, of course, is online. There is any question that you would like to transfer to Andrea from your side? If so, you just send a mail.
Can you allow me to share?
Way too big.
Okay.
Yes. Oh, yes, but there is some delay.
Delayed, yes.
Okay, good morning, everyone. I will try to show from my laptop, which from GoToMeeting, because it was impossible to connect my laptop projector, so there might be some delay on the slide. So I will speak about artificial intelligence in astrophysics. I think this is a very hot topic, and during this conference, almost every day we listen about some application of AI in astrophysics. So this is becoming a very hot topic in all the fields. So in astrophysics, that is going to change many things that we know in astrophysics. So here I try to list some of the key applications of AI in astrophysics, but I'm sure that there are much more, but it's just personally what I found. So of course, the first point is data analysis and modeling. So traditionally, for a very long time, the source classification via the pattern recognition are very powerful tool, and we are able to classify new stars, galaxies, AGNs, transients, etc. Very recently, so these surrogate models, which are for modeling the spectral energy distribution or emission spectra, are becoming very popular. Of course, AI is also applied in the observations and signal processing. For example, in processing of raw observational data, you can apply the AI to calibrate noise reduction, signal extraction, also for anomaly and transient detection, for example, to detect the supernovas, the big pictures of the observations, and of course to improve the image that we are looking. So there are many different studies that this image recognition is very fundamental, and of course they are also popular and very effective for the simulations. So they are helping to make faster your simulations, or they are used to schedule some observation, to point different direction of the sky, or etc. And of course, very lately also this natural language processing, which is becoming very popular, and they can help to summarize and make some summary of the scientific texts that you are interested. Of course, I am not going to cover all of these things. This is a big topic and very different. So my talk will be two parts, and initially I will speak about the surrogate model, how you can use to model the emission spectra, and in the second part I will speak about this generative AI, how this can be used to help research in astrophysics. So I will start with the first part is about the slow-down models, and these are about blazars. So this is the content, the structure of my presentation. So it will be about what are the blazars, why they are interesting, is the past, about the present, what the current multivariate and multi-messenger observation show, and what are the limitations, and why we need to have these neural networks to help to understand these sources. So this will be about kind of the future, what we can do with this neural network. So very brief introduction about blazars. So if you take any textbook, the basic definitions of blazars, these are the blazars which have the relativistic jet that is pointing to the observer. So if you take any catalog of blazars that show blazar like future of the sources, you reach number like 6,000 or 5,000, 6,000. So now the question is why these objects are so interesting, because if you compare 6,000 with the total number of galaxies that we know, between 100 and 200 billion, this is a very small fraction. So why there is the common view of the people that they are trying to understand the small number of the sources. So yeah, I list some of the points that I think are making blazars very interesting. So the first, all these are high power, the most powerful non-explosive sources in the universe. I mean, barometric luminosity is around 10 to 49 per second, and we are constant over the time. They have this relativistic jet that is strongly Doppler amplified. It means that we can detect the sources even in very far distances. This jet is most likely powered by the supermassive black holes. So when you study this jet, this is the exact way that you study supermassive black holes. There is this fast variability of the sources. And of course, what is interesting is the broadband emission goes from radio to very high gamma ray band, so all the windows of the magnetic spectrum, and plus, very recently, so the sources are interesting for multi-messenger astronomy. So some of blazars are associated with neutrinos, which makes them more interesting targets that you can study using two messengers. So one of the most interesting features of this object is the variability. So what is variability? That the emission is changing over time. So in this very nice presentation, animation, so each dot here in the sky is blazar. So if you see that the size of the dots are changing, so this is real simulation showing that sometimes you could have a very bright object and sometimes it really disappear from the sky. So this is the variability nature of the sources. So as you can see, one of the times this is very bright, it means very powerful, large flares, several orders of magnitude, but in some period they really disappear from the sky. So this variability is true not only in one band, but also in multi-wavelength observation. So here is shown the light curve on different bands, gamma ray, X-ray, optical, radio band, and you see that in all the bands you have this large amplitude of flux changes. And here also the spectrum, the corresponding spectrum is changing the so in so it means that even if you observe a blazar in one period, if you compare with the second period observation, you might see completely different picture. This is why what makes this topic more interesting, because you need to understand what is the origin of this variability. And of course, this variability is not only affecting how the sources, the physics of the sources, but also how they appear in the sky. So this is the source that we call the strange case of this object, because this is a very interesting blazar. So if you look any historical X-ray data, or you see any gamma ray data, you never see this blazar was not active, so never was observed in all the skies always in X-ray band. Suddenly in 2018, it starts to show some sign of the emission, and around 2018 it becomes extremely bright source in the sky. And for 1 year and 1.5 years, it was very bright object, then it disappeared again from the sky. So to demonstrate how bright it was, so this is the yellow data. I don't know if you can see the yellow data points here shows the X-ray emission from Altair 501, which is one of the most bright galactic sources in the X-ray sky. And as a comparison, the gray is the green one is the X-ray emission of this object. You see the amplitude of variability is even much higher than on Altair 501.
But instead you observe a variability. So how are they correlated?
Simultaneous. At the same when it was bright in the GV, start to emit also in the X-ray band, and both bands they disappear in after 1 year. So this is the how this emission changes over time. So initially there is no detection. You see that there is this very bright emission in almost all the bands, appearing in X-ray, optical, gamma ray bands. This is the period of the activity. This is the light curve in the gamma ray band, and after this activity, the source is disappearing again from the sky. So this is why we believe with Paolo there is this case called transient blazar. So sometimes they can appear and they disappear. So if we are lucky, we have the X-ray or sky monitoring on that period, we can see them. So that we believe that the number of the blazars is much more than what we believe from these traditional catalogs. So, of course, the key point is to understand what is the origin of the emission. And of course, we can do that using the messenger. So, the information that we can get from the astrophysical sources are from these four messengers: gravitational waves, photons, cosmic rays, and neutrinos. Interesting, if you put in one single plot, you can see that the frequencies go more than 50 orders of magnitude from all of these messengers. Of course, we don't have a single source that we can get information from all of them. But if you take the classical messengers, which are photons, and you put the emission spectrum of the blazars here, you see that they fill all the electromagnetic spectrum, which is nice, just from a theoretical point of view. We can put all of this data that we are observing in different bands together and try to understand what is the origin of it. If you ask what is the origin, so from theoretical point of view, I want to mention this model because this is the foundation of the neural network that we do. So there are two models. One is electronic. So according to this model, you have this double structure that you see from laser observation, the one peak here, one peak here, is interpreted by the emission of the electron. So you have the electrons that are injected in this compact region inside the jet. Why compact? Because there is this fast variability. If there is variability, it means that it's coming from the compact region. And from the interaction of these electrons, the low energy component is the synchrotron radiation, while the high energy component is the inverse contact scattering. And of course, but this is the general definition of the model. So depending on the state of the source, for example, if you have a different state of the emission, so this is Markov 541, you see this is one period when it was a low state, this is active state, a completely different spectrum, and means that maybe different zones are contributing, or depending on where is your emission region located, for example, different external photons also could somehow contribute to formation of this energy component. So this definition is a broad definition of different components that can contribute to your overall emission. If we come back to this window of astrophysical messengers, very recently we are able to study blazars also to using this window over here, which is the neutrino observation. So we are getting signals from some blazars. So now the question is, we see this electromagnetic emission plus this information from the neutrino observation. So what is the origin of this emission? Of course, if you have neutrinos, you should have a photon, because you cannot produce ultra high energy neutrinos only with interaction of the electrons. So again, in this case, this emission is produced from the injection of both electrons and protons. These were protons to produce the neutrinos. So again, the first peak is with the synchrotron radiation of the electrons, while the high energy peak, the second peak, is due to the interaction of the protons. So what is happening here? Actually, you have the protons that are accelerated in the jet to ultra high energy. They are interacting with low energy photons, producing these charged and neutral pions. And from the decay of the neutral pions, you produce these ultra high energy photons. But they are not escaping from the region. They start to interact themselves, produce electron-positron pairs, they interact, produce photons, and so on. So you have the electromagnetic cascade that is developing from this channel. You have the same cascade from this channel, plus neutrinos that are coming from the interior unions. So why this is interesting? Because now when you have the data and you want to constrain your model, you can do it not only with this electromagnetic component here, but also from the constraint that you have from the neutrino observations. So this 2 years that these studies are already possible because there were some neutrinos that were coming from the direction of the blazars. So okay, the first one is, we cannot read the name here, but it's Texas 546, this famous blazar that was flaring when the neutrinos were observed. And after this, there were several events that were detected from the direction of the blazars. But here I would like to talk about this particular source that has been observed. So what is interesting, so in 2021, December 8th, there was an announcement from the ISCO collaboration this year that there is an observation of neutrino with energy 170. Of course, this is not very exciting because there were neutrinos with much more energy. But what was interesting that after this announcement, there were other 3 instruments, in total 4 instruments, Pakistan, Baikal, and KM3net, also the European project, they all reported to the observation of neutrinos from the same direction of the sky. So up to now, with the neutrino astronomy, we were working only one event. So now we have the multiple instruments that they are detecting events. This is actually quite interesting. So we start to look at the direction of the sky, and we saw that near the uncertainty region of this event, there is a blazar, PKI 0735. If you look at the multivalent data, it's kind of normal. There are these minor flares, which is okay because we are looking for a blazar, no? But this is actually before the neutrino observation. So if you look when the neutrinos were when the neutrinos were observed, this red line over here, you see that in all the band, in the gamma ray, X-ray, optical, UV, it was flaring extremely, the highest flare of the source ever observed. So if you zoom, these are the different lines, show the different periods of the neutrino observation by different instrument, and you see that the source was extremely flaring. In X-ray band, it was so fast that the different snapshots of the swift observation show the change of the flux variability. So if there is a source which shows a neutrino emission and there is this multivalent variability, it means that some hadronic processes are taking place which are producing the neutrinos. This is where we develop some models and we explain both how this emission is originating and how to explain these neutrinos. Okay, even though the blazars were very long under the investigation, making some multivalent campaign, they are very key unresolved issues. So here I try to put some of these problems that they are still not solved. So it is like the launching, collimation, and propagation of the jet, what is the composition of the jet, the magnetic field structure, what is the evolution and the jet of this, energetic of this jet, what is the particle acceleration mechanism, what is the dominant contribution of the emission of the electrons or protons, what is the origin of the flares, which mechanism can produce flares ranging from minutes to years. So these are all some main components which are the part of the puzzle that we need to really put together to try to understand this of this blazars. So of course to do this we need to have these observations and we need to have the theoretical modeling. So only with the theoretical modeling we are able to understand all of these questions that I have. What is the status of the current model? So in the past 20, 30 years there was a huge development to develop different numerical models, different boards that they are really able to nicely explain some features that we see from the sources. So what you do is you select 1, 2 periods, like one normal and another flaring period. You model this within one lepton or hadronic scenario, and then you are trying to understand some properties of the source. Of course, these are good that you are able to recover some information about jet energetics, about general properties about that. But the question is, this modeling of this 1 or 2 periods is enough to understand the source? Of course, it's not enough, because if you plot here the frequency flux versus the time in this 3D plot, you see that in different periods the emission spectrum of the source is changing dramatically. So if you model one of these or this one, then you don't globally understand this object. So the data is much richer and contains more information. So you can do better job here, and in order to truly understand these objects, you need to fit not only one period, you need to model not only 1 or 2 periods, but you need to model as much as simultaneous ACDs that you can get from your data, apply some theoretical models, and you can see so dynamically how this is changing. But for this, you are required to have data fit. So what is the issue? This is a very well-known issue. What is the problem of this fitting? So if you have a numerical code that is fully, so takes into account the injection of the particles, the cooling, the propagation, all these processes, then your numerical codes are good because you are able to explain the process. But on the other hand, they are a little bit computationally heavy. So, for example, if you have the assynchronous photon or external photon model, the traditional codes used to run for one parameter space between 10, 20, 30 seconds, okay? From the point of view, this is nice, no? You put the parameters, you push the button, in 30 seconds, you have the information. But if you are doing the Bayesian fit, then you need to compute 10 to 4, 10 to 5 times this parameter space to check different parameters. No, it means that this computational time is becoming extremely long. And I'm not speaking about the hadronic models that are way more complicated and take more time. But it means that you could wait up to like 3 months to get some fit result for one period. But this is not good because you can put a lot of resources in this computation. You try to model one data. After 3 months of computation, you have to just throw away this computation because you cannot use it for another sources. So this is where the machine learning is going to help a lot. Because why? Because with machine learning, what you can do, you can generate models that they can predict your emission. You can use these models instead of using numerical code. The important point here is that you can make a computation once, and you can use for different sources, for different periods, etc. So this is very new and very active. So in the past 1 year, we were publishing 3 papers on this direction, trying to build different models that can explain, can be used for the fitting. So let me to show what I mean and how you develop this. So let's assume you are considering starting from open model. I mean, I don't know if you can see the name of the parameters, but these are the 7 parameters that are free in the model. No? For these parameters, you consider the most realistic limit that you can, from low possible one to the highest possible one. And you consider some range of these parameters. Then you use these parameters to these 7 high-dimensional parameter space. You use some statistical methods to select from the subset of the parameters that they are covering your region of your parameters. No, there are something, etc. There are different statistical methods. So you select 2 million from this parameter set. You put in your numerical code. In our case, we use Soprano, which is the numerical code that we developed in collaboration with Damian, which is meant to understand the processes in relativistic sources, like your BIS or like Blazar. So you put as an input in your numerical code, and you compute the spectra. So you compute 2 million spectra for given input parameters. Then you pass these input parameters with your computed spectra to the neural networks, and the neural networks are looking at the connection between the input parameters and the output, which is the spectra. They are learning this connection. Then, as soon as they are trained, you can use the observational data of your neural network to make some fit, and you are able to use this neural network instead of your numerical code. So in our case, we use this convolutional neural network. So these are the classical networks that we always use for images, but they are understood that these are good also for time series analysis. I don't want to describe the structure of the network that we built. So this is the input parameter, that are the model 3 parameters, and this is the output, which is the spectrum. I would like to show you here what means the training in this case. No? So on the top is the spectrum, and here is the layer. So this is just demonstrated in 1% of the total database. So in 1% in 2 million. So if there will be some difference between the trained and the observer and the spectrum, but this is because it's used only in 1%. So if you look at I couldn't do this in 80% of the total database because the simulation would be very long. So here you see that initially it's off, but it tries to adjust all the layers such that they become the green, and they are able to explain this the spectrum that we are observing here. And each step, this is improving. So this difference, as I mentioned, that in 80% of the data set is improvement. You don't see also this offset. So it means that once you train it your neural network, you have that each of these nodes is able to recover the information from that part of the spectrum. And this is the general workflow. What is the key? What is important here? That I mentioned that numerical models use around 30 seconds. No? With trained neural networks, the same thing can be done within 0.04 seconds. So 1,000 times you make everything faster. It means that now you can easily do the Bayesian fitting with this neural network. So here is the modeling of this spectrum of the marker 421. You see that there is this nice explanation of the data, and here you can also see this posterior distribution of the parameters, and you can see how the parameters are connected. You can try to see the properties of the sources. So this is another CNN that we developed for external inverse control. We model this emission from this family Blazar CT102. What is interesting, we are able to look at the global all the parameter space. We saw that there is this double structure in the posterior distribution. So there are two models that they are statistically better explained. So this network that we have developed are also available for everyone. So in our data center, you simply can come to the web page, because the part of theoretical modeling, you can upload your data, any data that you like, that you want to model. It appears here. You just provide the distance of your source, and you just your email address, and you can just put the button feed, and everything is done in the background. So as soon as the feed is finished, you get another email saying, okay, your feed results are ready. You can just open the link, and you can see the modeling results where you see all the parameters. There are the corner plots, everything, all the information that you require for your study is available and provided to you. This is very actively used by everyone. So this is the whole user map of the data center. You see that we are covering almost all the parts of the world. So we have active users from everywhere, from European countries, from Russia, China, USA, from everywhere. We're very active users that are downloading all the data and trying to make the modeling. I think this is a nice indicator for us because it means that whatever we have created is actively used by everyone. And this is why now we would like to really improve this. But as I mentioned, our goal is not to just model the 1 or 2 periods, but with the CNN, we are able to also scan through all of these vectors and try to generate as many ACDs as possible, and we can just see in the time how this radiation is changing. So this is this object, OJ287, that I will speak a little bit more in the last part of my presentation. But what we were able to do, we were able to investigate this, how the variability is transformed to the physical processes, and see different components how are changing over time. This is very important that you can study dynamics of how the radiation is changing over time. So up to now I was speaking about the electronic model. So if now we come back to the hadronic model, as I mentioned, for hadronic model there is this big problem because first of all they are computationally very difficult. So if for one parameter space, it runs like 1 minute or 2 minutes, and there are other pods that is several hours. So it means that up to now, no hadronic pod, there are limited groups in the world that have this hadronic pod, like 5 or 6. But none of them was able to make really fit because it's computationally very difficult. So if it is like 1 hour of the time, if you put any fitting engine, Markov chain Monte Carlo or Martinez, you will never be able to make any fit because the time is very low. Otherwise, you need to use the supercomputer for a very long time. The only way that they were doing is to make some assumptions. So they were fixing several parameters in the model, leaving 1 or 2 parameters available, then it is computed faster, so you are able to make some reference. But the problem of how to generalize your assumptions. So if you fit the spectrum of the protons, you fit the magnetic field, and whatever information you are getting is very limited. To demonstrate this, this is a hadronic spectrum. This is neutrino, this is the electromagnetic component, only when one parameter is changing. You see from here to here is very different spectrum. So if you make any assumption and you fix one of these parameters, then any fit that you are obtaining is, in my opinion, meaningless because you have made an assumption in the beginning. So this is where also we try to train the surrogate model for the hadronic models as well. So this is where you have to take into account all of these cascades, the propagation of the cascade. So the parameter space here is 10 model parameters. It's much more difficult. So this is why we generated 7 million spectra, and we trained this neural network on this 7 million spectra. And for this, we use the supercomputer in Armenia. For 2-3 weeks, we were making fully easy this computer with a lot of complaints, but we finally managed to train the network on this hadronic model. So this is how the result from the validation and training sets. You see that for very different parameters, we are able to recover to explain the data set. So you remember I told you that it was impossible to make any fit, but now, because of this training of CNN, we managed to make the fit within 3 or 4 minutes. So from something that was really impossible, now in 3 minutes, you push the button and you have the complete check of the parameters, and you are able to fit your spectrum. Moreover, we developed 2 different ways of making it. So the first one is when you provide the neutrino spectrum. So you say, okay, I have this energy neutrino, and the second one is the number of neutrinos, because sometimes in the neutrino observations, you are getting information about the number of the neutrinos that are observed. So in the case of Gaussian likelihood or the Poisson likelihood, we are able within 3-4 minutes to make the fit and provide you the spectrum and provide you also this posterior distribution. So this is a big change because up to now there was not possible to do this thing. Right now you can in 3-4 minutes make this, which is very nice. So now I would like to move to the second part of my presentation, where I will speak about this natural language processing for scientific tests. No? In my opinion, when there was the launch of ChatGPT, imagine it was not just a product release, no, it was a paradigm shift. So because after this, it transformed how we deal with machines, how we deal with artificial intelligence, and it accelerated global innovation across all disciplines. For sure, this will affect also science, different fields of science, including astrophysics. So up to now, the traditional AI methods were very effectively used in astrophysics. No? This pattern finding, classification, different methods were very effective. So they achieve some results that humans never achieve because they are fast, they are able to check different patterns, they find very interesting results. So of course, these traditional tools are very effective. So the question is generative AI, which generates new data based on the data that is trained. Can it somehow help in the research or not? So if we answer to this question, we need to define what is the research. So I mean, this research is an ecosystem of the contribution, no? Where you have the experienced person who knows the field, knows everything, and you have these young researchers which know all the details, you know, the coding, etc. So they can go. This experienced person is defining the problem, and the young ones are going to solve it. No? But in this ecosystem of the contribution, this generative AI can make really very strong contribution. Why? Because there is this exponential growth of the scientific literature. No? So even if you are the most experienced person, it is very difficult to keep the track all of this development. Generative AI very easily can make a summary and provide the information. Plus, the generative AI, of course, can help you with this coding, providing new ways of doing it, improving your process, etc. But of course, this doesn't come for free. What I mean, you cannot just take the commercial LLMs that are available and you use them for your pocket. They can somehow help, but if you want to have a really impact on your research, these commercial LLMs, although they are very good, but they are limited. So here I list several of the problems that we think that is the problem. First of all, the scientific accuracy. So we know that these commercial LLMs can hallucinate. You know, they can provide you some answer that is totally wrong, but you don't know way how to check it. Second, they lack the domain knowledge. If you ask a very specific question about very specific terms, sometimes they make no sense because they are not able to follow your question. They are unable to handle the messy or multimodal data, no? The data that we give in astrophysics. Sometimes you need to convert from here to there, etc. So they are not able to handle this data. Model integrations. No commercial LLM allows you to make any modeling. So if you ask about specific processes, you can get very nice definition. What is synchrotron radiation? What is synchrotron radiation? But you will never be able to make any modeling or any fitting using these commercial LLMs. And of course, there is this problem of transparency. So if you get any information, you don't know the source of the information, no? Because you don't know from where it is extracted. And we think this human in the loop that can really contribute, or experienced people can contribute to make these languages more acceptable for everyone. This is where we would like to introduce this tool called Astrogenesis. This is something that we are working with my group. So if you want to have a very technical definition of Astrogenesis, so Astrogenesis is an LLM-powered multi-agent research assistant that integrates retrieval augmented generation, multimodal data access, and domain-specific reasoning for astrophysical research. But if you want to go to simple word, it's public available web platform where data, information are very regularly updated, where anyone from students or experienced researchers can explore the latest discoveries in any field in astronomy, can use this tool for their modeling, they can use for getting data, and etc. So this will be an assistant that can help you with your research. Now, if I put in this same diagram the advantages of Astrogenesis. So here we are using this RAG method that we are taking the information only from the scientific articles, so we minimize the hallucination. So since this is built for astrophysics, it contains all these domain-specific applications. It is built to handle the multi-wavelength and multi-messenger data. There are these neural networks that we have trained, and it can use it for the modeling. It provides the full citation and reference, so you can check where the information is taken. So if you work yourself, you can go there and check it. And we implemented this user-friendly interface. So if you are getting some answer where you can give us feedback if there is any problem, so the expert can review and improve the language, the large language model. So this is not, what I mentioned is not so simple. This is the full architecture of the system. This is a very complex system that we built. So here there is this central supervisor agent. So this is the main brain, the main function of the system. No? So if you ask any question, this system is making decision where to send, which agent to send. So if you ask some specific information about some detail, it sends to this literature agent, which is then performing the search in this vector database where they are embedded of these scientific papers. It finds that the top 25 papers which have the maximum potential. Then what it's doing is making re-ranking. Re-ranking means that it takes the question of the user and the context of this paper and tries to see which is the contextually more relevant for the answer. It collects the top 5 of these re-ranked papers and passes back to this agent. The agent is beating the answer based on whatever you ask it and provides you scientifically accurate answer. The next agent here is data agent. So if you request any data, so you say, I need this data. What it's doing is accessing the public databases or some databases that contain pre-trained, pre-analyzed data and gives you back the data. Now, not that in the future we are connecting this with the raw observational data. So if you request anything, it will very fast analyze this data and bring you back to the already science-ready data. This is good because it will shorten the time from the observational data and use of this data. The other one is the theoretical modeling agent. So if you require, you can ask to model any data that you recorded. So it passes to this agent, which is performing this modeling using this neural network and brings back to the answer. And this fourth agent that we have is called a hypothesis generation agent. So the idea is something like if you want to study some specific object, but you are unsure what can be done, it can look to the trends of other published results, what have been done to other sources, it can give you some suggestion what you could do there. So of course this is not going to replace your mind, but it's going to give you some direction where you can do what you can do. Or for example, you submit some data to fit, you say, okay, fitting testing a long-term model, it can quickly test the other model and can answer to you that you know that your data can be also better fitted within this model also to look there as well. So this is just to give you some indication where you can go and what you can do. And what is the most important in this configuration, that this multi-model structure is scalable. So if tomorrow we want to add a new type of the source, this new functionality, we can just connect to this central agent and we can just move. To demonstrate how this works, I have this video over here. So this is not public yet, so this is just in a Streamlit. We are going to make it public within 1 month or so. We are working now on it from that. So look, here I am asking very specific question. No? What physical conditions are required to explain the 2060 TV flares of blazar, this specific blazar, and how ones on SEC and harmonic models compare in terms of Doppler factor, magnetic field, and jet power? This is very specific question. No? If you are really interested for specific object, specific flare, etc. If you ask, now what is happening, the system is going to look in the scientific articles, and from these articles it's taking the information that you requested, is building the answer and brings you back the answer. You see? So it found the reference, it made the summary of all the parameters that you requested, and for all the models, and brings back to you that and gives you the reference that you can go and study yourself. So now if you ask, get the ACD of the same source, so you are interested and you want to see from data-wise, so it brings you back the data. Then you can ask, okay, I want the same data, but only for the period between 01 January 2019 to 05 January 2000. So you know that specific period that you are interested. Again, this is going with this agent and bringing back you the data that you can see here. But now more, okay, you got the data, but you are saying, okay, I want to model this to understand what is going on. No, you can just submit data and you ask to this large language model the attached data. No, but this is not enough information. No? You are providing something that is not sufficient. Then it comes back to you, try to clarify what else it should do. No, it asks, okay, which model should I use? Synchronous Compton, external Compton, hadronic, and also the redshift of the source, because it has a missing information that it doesn't have. So as soon as you provide the model, you provide the redshift, and you provide also about whether it's a galactic background like or not. Then in the back, it is connecting to these neural networks, performing the fit in the backend, and sends you back the read answer. So sends you the back the fitting results with the corresponding parameters, and asks you what you want us to do. If you want to discuss the specific parameters, we want to compare with the previous publication, or etc. So what is that in the morning you can open archive, you see some sort of studies, there is some modeling. If you want to test something else, you can just get the same data, apply different models that you want. In 5 minutes, you can have a several equation, and you can just compare with the published result. This is the timeline of roadmap of the implementation. So that by the maximum the end of this year, we'll have the full of this model ready for Blazars. It will be public with this full web page of Genesis AI. And then our midterm goal is to move to other class of sources, to GRB supernovas, like binaries, and also like etc. for fragments. And long-term goal is to just extend to include other areas of physics, other research areas, which would be interesting. So this Genesis is a new vision where for discovery, for new era of astrophysical discovery. So will be Genesis will be a research assistant that will make it the simpler and the complex possible. Because before Genesis, if you wanted to make some multi-messenger data model, you needed to find someone that has someone has a computational resources, someone is ready to do it for you. You need to take like 1 year or so. But with Genesis, the same job that would require a lot of time, now you can do the very simple command. You can say model the ACD of text after 5 simple things in natural language. It is very simple natural language. This will be done in 3 or 4 minutes. And imagine that everything will be possible to do with all areas of astrophysics. I think this will be very powerful, and it will help everyone in their research. So, in my opinion, this neural networks or AI or generative AI generally is going to change many different fields. Of course, in our daily life also, in science, and I think astrophysics will really be able to benefit from it. And in the future, it will be very helpful, and we can do many things from our laptops using these tools of AI. I have been asked to show a few slides also about this particular source. So this is the paper that we published a few months ago with my ex-student and collaborator Damian. This is about this Blazar project 287. So our idea here was to understand what is the origin of this multi-valent emission, and for this reason we.
This is the one
yes.
that discussed by Valtone.
Yes, Valtone.
Okay, can you slow down a moment?
Yes, I can slow down. This is the multi-valent vector which we use. So this is gamma ray data, X-ray data, optical data, UV data. This is another optical data, and infrared data from WISE. So here our goal was to see how the multi-valent spectrum is changing over time. So here you can see that this is in-time propagation, and here you can see how the different components is changing. So from this, what we did.
Again, what you have on each line, different energy.
Yeah, this is the flux. This is the time. This is gamma ray band.
Gamma ray.
So you see solar flux. This is X-ray.
Yes.
Swift. This is UV band. This is the optical band. This is also optical band. See, you see that there are these flares in different bands.
But they are not coincide.
Yes, they are
not a different type.
Exactly.
And what about the luminosity? If you compare the energy of each one of these flares, the energy of the flare.
I mean, I have here the flux. Okay, for the optical, I have the energy in Earth, so it's 10 to minus 11. So this is the 10 to minus 11 here. I don't remember the luminosity because I don't remember the I can tell you
exactly, because it's not enough to see that, but we need to have information about the energy in this flare.
Okay.
And from the time the luminosity evaluated the energy to understand their significance.
Okay.
And in particular, in the case of Altona, they were looking at this system and for many years and evaluate.
This is some animation from their paper. So I didn't read the paper, but I think they did the infrared band observation. I don't know if you can see that this is, according to the simulation, this is a black hole that is orbiting. You see, this is that appearing. This is the big mass black hole, and this is the smaller mass one. You see, this is from this paper that is. He's one of the co-authors. Actually, this guy has like maybe 100 papers only on this source. So I think this is one of his favorite sources. So they use many different observations, as you mentioned, like very long optical observation, and they see that there is the periodicity of the signal between 10 to 11 years once it is repeating. And this is how they interpret that this is the orbit of the second black hole.
Yes,
we don't see this in our data set because the instruments that we use are not so fine to see. They are using the Spitzer data, which is an infrared and have this very nice angular resolution, but they can really point very close to the central part. And they infer some data. I didn't have to check with this paper, I will do it, but this is what I found in the web from their publication.
yes, but the problem there is that they look on the emission of gravitational waves in the long range, and it's necessary to see this flaring activity, how much it can affect the dynamic of the system. And this, I think, is crucial. Therefore, it's not only to see now on this type of source, we start to do real physics. Therefore, first of all, the determination is not enough to say that in this object there is a flare in the JEV, in the X-ray, and the optical. Yes, that is okay. But now we have to do the overall energetic accounting of the system, and in particular, the determination of the mass of the system. And certainly, in this sort of system, like Guangqui is trying to do, not for this system, he is doing that for the quasars. But also in this sort of system, we need to know what the role of the dark matter is in creating such huge black holes. Not only one black hole, but two black holes in the battery. Therefore, one who is looking for the moment to the single black hole, but there will be the problem to look for. But what my message is that this meeting, for the first time, we are people speaking about the physics of not only the time sequence of the flaring activities, but to give the attention to the source, to the black hole, to the dynamic and to the moment of formation, and to the role of dark matter, which is very important. This is the first time which happens with respect to the previous work, which is very beautiful. But I think now we have to address the real problem, because, for example, from the gamma ray, we have now, for the GRB, for example, to take an example, we have very clear difference between JEV and X-ray activity and gamma ray activity. And in this system, for the first time, we have understood the interface of this emission. And this is a fantastic, clear result, which this philosophy should be brought to these systems. I mean, there is this new phase coming out. Up to now, we're just observing, but even without looking at the energy, the luminosity, and all this correlation, we have example in this meeting which can in other system which indicate a new style of research. And of course, all the things you are doing is absolutely essential, because to have the possibility to check immediately the paper published and everything to be at the disposal is an enormous opportunity. Without that, we could not do anything. But what I'm emphasizing is the first time that we are narrowing on the astrophysics.
Yeah, about that, I would like to mention that this is the kind of collaboration that we are starting with Caltech and MIT. So I think this is quite significant also, because if we have this strong contribution from USA, up to now it was only in Armenia. Already for some time we are starting this collaboration with MIT and Caltech. I think it would be very significant.
Definitely. I'm sorry, I exaggerate I forgot my duty as a chairman, and I was speaking personally. There are only. Yes.
The astro management thing have a philosophical action. So the fact that it model source so successfully, does that mean that our physical understanding already pretty complete? And if so, would that minimize in a way we're biased against mirror things that may be potentially.
Yeah, I think this is a great point, because you are right. I think what not only astrogenesis, whatever is done in this is done in the scope of some specific models. No, I mean, unfortunately, we have two parts of the one that we can let the network to decide for itself which model is better, or if there is something that we don't know. In my opinion, right now, if we give this possibility uncontrolled, it might find something that really does not make sense. But I agree with you, this is kind of limitation, because we are just able to take within some models that we humans develop. But I think in the future, maybe like in 2-3 years, when these models will be already possibility of self-learning, it will be possible to test these kind of things as well.
Possible for the time being to allow for a function that just allowing the model, allowing the AI, when it at some point recognize that, hey, I cannot find you a good fit, but tell you that.
Yes, this is possible. So in our interpretation, so we would like to make this possible. You upload the data, you ask to pick for something. No? Your model fails, it's quite the other one. If in the end not able to produce any meaningful result, it will tell you, okay, I'm sorry, I am not the answer. And this is already a good point, because if you are able to find data that is not possible to interpret with current models, it means that you are looking something new, and that you as a human can make any decision in that regard. So you don't need this to the AI, because they make some crazy things, but you, using your brain, you can go to that direction, which is, I think, a very good point, because allows the people, okay, even it's important to identify something that is not possible to explain by the current model, so you are not doing saturation force. No? If you are able to find this kind of data, this is wonderful, and you can get produce new models or new ideas. And I think this is, since it's fast, it can do many different checks. No? But if you run the numerical model, if you have 10 models, each time you need to wait 1 week or 10 weeks, you can't do this. But now with neural networks can do very quickly all the checks, and in 15 minutes you can after all.
And that would be critical. That would potentially accelerate the pace of finding, because the machine solve all the known problems.
Exactly. This is why we have this hypothesis generation algorithm. It is helpful for this kind of case. No? Just to try different models, try different hypotheses, and suggest you something. Okay, I'm not able to take all group this direction. There is this interpretation which is better. This way that the researchers can get some indication where to look or what to do.
You have the question,
The high model hexagon, we can talk during lunch dinner.
but it's okay, you can.
Because I have many questions. We discuss it.
No, but for the other people, at least mention some
The
of the
most important question.
the most important.
The most important question is it inspired me a lot. Yeah, then we can do something else.
One of the most important things that I forgot to say is academic is community based. Although we are the code that do this, we are super open for everyone for the collaboration because we believe we need the contribution of everyone to be something that is useful for all the researchers. So our goal is that like in 1 year maximum to make a kind of workshop where we invite many people and we ask what else do you want, or why do you want to contribute, or what else we can do. And we are super open for all the collaborations. Of course, with you, we have to do many different things.
Okay, if there are no more questions, and we will leave to minor interruption, let's go to Manuel Hoffman. Manuel, are you online? Can you?
Yes, hello, good morning. Let me see whether I can share everything here.
And see you. Now in a moment we will be able also to hear you.
Mm-hmm. Okay, can you hear me already? Okay, I see you're switching in more volume there.
Okay, Manuel, try to speak.
Hello, can you hear me now?
Yes,
Very well.
yes.
Mm-hmm. Okay, very good. And let me see whether you can also see my presentation. You should now also see my presentation.
Yes, we can see it.
Mm-hmm. Okay. Yeah. Good morning, everyone, and greetings from Paris, from Sorbonne University, from the Laboratory of Nuclear Physics and High Energy Physics, where I'm right now. I'm very sorry that I cannot be present in person because I was attending here a conference until yesterday. But I'm very grateful for this opportunity to give this presentation online, and especially my thanks to Remo Ruffini for inviting me to give this talk here. So what I would like to discuss during this time is part of theoretical physics. So I would like to talk about some phenomenology that we can derive from theoretical physics, and that is closely related to what we have just heard, actually, namely about the physics of black holes and matter around black holes. So what I would like to discuss in particular is how we can find effects from quantum gravity in the matter dynamics near black holes. And since this is a rather theoretical topic, I will give a more general introduction to this topic and then explain and show some preliminary results that we have on this topic, and where this could lead in the future, for which kind of future research and possible tests. So let me start with a very brief introduction and motivation. So why are we interested in these kinds of physics? So my background is from gravitational physics. So we would like to study problems in gravity and cosmology, in particular trying to model with gravity the accelerating expansion of the universe and also the homogeneity of the cosmic microwave backgrounds. So we know that we have models for these observations. Most well-known model is the cosmological standard model, the lambda CDM model, that uses dark energy in order to explain the accelerating expansion of the universe. And we have the inflation at the beginning of the universe to explain the homogeneity of the cosmic microwave background. But we don't really know yet what are the physical mechanisms behind these models. We can understand these maybe as effective models, but we do not quite know yet, is it some unknown type of matter that is driving these effects? Is it the modification of laws of gravity? Could it be, for example, a scalar field that's in addition to the metric that mediates gravity? Or could it be even effects from quantum gravity that we see here that become manifest at these very large scales? And here, the idea that I would like to convey here is to look at the modification of the geometric structure of space-time. So basically changing the way how we describe the geometry of space-time. And well, as in general relativity, the geometry of space-time is very closely linked to gravity. So we use the geometry of space-time to describe gravity. And basically here, by changing the geometry of space-time, we also change the way how we describe gravity in order to explain these observations. So this is actually quite similar to replacing a flat space-time by a curved space-time that leads us from special relativity to general relativity. Simply by changing the geometric structure we use in order to describe the universe, we can incorporate gravity. And here, basically, this is just taking this another step further. And in order to describe the matter, we also need to find a matter model that is fit for this geometry that we use. So in the GR general relativity, we often use the perfect fluid model, for example, which then can describe the matter, for example, near a black hole. But here I would like to use different model, so-called kinetic gas model, which we can understand as a velocity-dependent distribution of the particles. And now the question is, of course, two questions that arise from this is, first question here is, if you use the kinetic model, how does this react to a gravitational field? How does the gas move in a gravitational field? And also the second question is, what kind of gravitational field does it generate if we allow for a more general theory of gravity? So in the general relativity picture, everything is quite clear. We have this fluid, we have an energy momentum tensor, and we can calculate the gravitational field. But if we have a different geometry and a different model for the matter, then the question is, how can we describe these interactions between matter and gravity in both directions, essentially? Now here, there is another question arising if you look at gravity theory and next to cosmology, and this is the so-called problem of quantum gravity. Main problem here is that we simply do not have a quantum theory of gravity which is complete. And the question is, how can we find such a theory? How can we quantize gravity? Well, if we start out with the same methods as in quantum field theory, turns out that this is not working. We find divergences, we find problems with so-called renormalizability, and we cannot proceed in the same fashion. Now, we could also try to just guess a theory of quantum gravity. So there are theories like, for example, string theory goes in this direction, or so-called loop quantum gravity. But this is not the easiest approach, but just to guess the correct theory from scratch, so to say. We could also assume that gravity is classical, or at least semi-classical, which certainly leaves some unsolved problems, or at least questions, then how to combine gravity with the other forces. Why is it so different from other forces if you simply make this assumption here? Now, the route that I would like to take here is to study effective models of quantum gravity phenomenology. So basically, not looking at the fundamental theory at all in this particular part of this work, but just looking at potential effects that may come from a fundamental quantum nature of gravity, and that somehow manifest themselves in effects that we can find in the universe, and that we can model via classical physics, actually. Very similar to effective effects that we find from quantum theory, for example, in a solid body, but we still can describe the solid object by classical physics, for example, elasticity or electrical conductivity. Now, how can we study such effective gravity models? Well, first of all, the idea is not to care too much about the fundamental laws of gravity. So what would be this quantum gravitational background? But we start from the assumption that general relativity is almost correct. By almost, I mean that general relativity certainly describes very well the physics of the solar system. It also describes the physics of laboratory experiments that we do on Earth, so on a very wide range of scales, actually. And also, if we go into the universe and we look at the physics of black holes or neutron stars, for example, we find that general relativity gives us a very good agreement with our observations. But well, we still should care a tiny bit, at least, about the fundamental laws of gravity here, because we would like to model possible sources of quantum corrections. So we would like to understand how can quantum gravity affect these classical observations. So we need to have at least some idea what could be the quantum foundations of gravity in order to figure out what would be the possible corrections to look for, possible signatures to look for. And then once we know these quantum corrections to the gravitational interaction, then we can study the phenomenology of these quantum corrections. So we can try to find effects that describe that are generated by these corrections. Now, how can we do this? So the idea is to find a physical system which very much amplifies the deviations from general relativity. So we need a system where these effects are as large as possible. And here the idea is to study a compact system with very strong gravity. So obviously, black holes are one of the systems in the universe where we know that gravity is very strong and is dominating the system. So it would be a possibility to use this as a test bed. Then, of course, we have to think of possible observables in the chosen system. So like we have just seen in this very nice talk, discussion of the light curves and emission of blazars are exactly something that goes in this direction. And then, of course, we have to calculate how the quantum gravity influences these observables. So what would be the imprints and how can we disentangle them from other effects like properties of the matter in particular. So here the basic system that I would like to look at here for testing this quantum gravity phenomenology is thus these gas dynamics near black holes. And I would like to explain a bit how to model these and how to model quantum gravity effects here. So the very pictorial view of how does this this whole machinery work. So how do we do quantum gravity phenomenology? So the basic idea here is that if you have a quantum gravity theory, we have some matter here on the left, basically, that generates a gravitational field. And this gravitational field is described by quantum gravity, and any other masses or matter that interact with the gravitational field react to this field, and then the motion of the matter depends on this gravitational field. So very much like this famous quote by John Wheeler that matter tells space-time how to curve, and space-time tells matter how to move. Now, the problem here is that quantum gravity is a black box. We don't know this theory yet, so we can only construct different models here, but we don't know yet which of these models would be correct. And so the idea of the effective quantum gravity models here is to understand quantum gravity as a small correction to the general relativity, at least in the regime that we can probe with our observations. So we just assume that the background solution here is given by general relativity, and we have a small quantum correction here that comes with some expansion factor epsilon. Now we still have a black box here, which is signaling that it's something unknown, but the idea is because of multiplying this with epsilon and treating this as a perturbation, we have less of a difficulty of making predictions from this unknown part simply because the contribution is small. Now, general relativity is, of course, a very simple theory. We can calculate this. We can solve the field equations. So this is something we can very easily work with. And of course, we know what's in this white box. General relativity is a known theory, so we know the equations and can handle them. So we only need to find out what is this quantum correction. Or to be more precise, actually, it would be nice to study all possible quantum corrections, because then we can actually discriminate them with observations. Now, how do we describe matter in these models? So what are the matter models that we use in these classes of theory? So first of all, let me give a brief recap of the matter model of general relativity, in particular here the perfect fluid model. And here the idea, if you look at cosmological symmetry, for example, then the perfect fluid is actually the most general energy momentum tensor that is compatible with the cosmological symmetry. It has only two variables. It does not have any shear stress, no friction, and the only variables describing this matter in the cosmological setting, at least, are density and the pressure. So we can set the pressure to 0, then we have dust or dark matter. We can set it to 1/3 of the energy density, then we have the radiation, and dark energy has this property of negative pressure. In particular, if this is here equal to -1, then we have this, vacuum energy or cosmological constant. Now here, I would like to look at a different model, namely that of a collisionless fluid mostly. It's also a model for dark matter, but the idea is not to describe this by a density and a pressure, but rather by an ensemble of point masses that do not interact with each other. So let's assume, for example, you can also describe them as stars, for example, or galaxies, assuming that the distances are large enough between them so that they do not collide, do not interact directly with each other. You can also consider, instead of these large objects here, you can also consider single atoms, let's say neutral atoms for simplicity, or dark matter particles that only interact very weakly with each other, or have at least a low enough density in order to be described by this model. We can also go a bit further than that. We can go to the interacting fluids, and certainly if we go to higher densities, for example, accretion disks around black holes, then of course we have to go to this model here and look, for example, at the so-called Maxwell-Boltzmann gas, which is basically described by a velocity distribution of particles. And this velocity distribution then corresponds to a non-vanishing pressure of the gas. But we can also go beyond that. We can go, so this Maxwell-Boltzmann gas consists of neutral particles, but we can go to a plasma, and then we have simply multiple types of particles, typically ions and nucleons, even if they are fully ionized, and electrons. And then each of them would be described by its own distribution of particles, basically. Now we can go even further. We can go to imperfect fluids. If we include shear, friction, viscosity, then we have a kinetic energy dissipation into heat. Or we can even go to other models if we have other gravity theories where we have different geometry. We might have additional properties of the matter, so-called hypermomentum, for example, which describes intrinsic properties of the matter. For example, the spin. The spin can couple differently to gravity in certain theories, but I will not look at these models here. I will mostly focus here on the collisionless fluid or gas model. Now, why are we interested in these kind of models? Well, there are actually many reasons for studying these kind of models. So in astronomy, there are effects. One is known, for example, as dynamical friction. So, for example, if you have a massive object that passes through a distribution of light objects, so for example, think of a stellar cluster that is passing through the galactic disk, then the gravity of this rather massive object would change the positions of the lighter objects. So, for example, the stars in the galactic disk, and this perturbation of the light objects then has some gravity effect on the massive objects. So, for example, as I mentioned, this globular cluster passing through the galaxy. So basically, as the cluster passes through the disk, it would attract stars. So the number of stars, the density of stars increases in the region that has been passed by the globular cluster. So it increases behind the cluster, and is therefore, because of this higher density behind the cluster, the globular cluster would experience a force that is slowing it down as it passes through the galactic disk. So this is one thing we can model with these effects. Another one interesting effect is the so-called splashback effect, which occurs when we have a gravitational collapse of a galactic cluster, for example. And then the galaxies would pass each other near the center of the collapse. And also here, because we have here objects moving in different directions at the same location, we need a different matter model to describe this. And here this kinetic gas model actually is a very nice model for describing this effect as well. Then there are so-called stellar streams, which are related to the first example here. If you have a globular cluster that is orbiting the galaxy and therefore passing by repeatedly through the galactic disk, then we have tidal forces acting on this globular cluster, and that will at some point tear this apart, and so we will have in the end a stream of single stars that are forming this stellar stream that is still orbiting the galaxy. Now also galaxies influence their environment, so galaxy collisions can have effects colliding gas, passing stars, or a galaxy can enter a filament or a galactic cluster, and this also has some influence to the environment. And finally, we also might want to describe the dynamics of the intergalactic medium. So there are such objects called cosmic gas highways, which are basically just describing the gas in and near the filaments. Also, in structure formation, there are certain singularities appearing that basically describe the that can be described by geometry of crossing sheets in the velocity space, so to say. Okay, so what is this model I would like to talk about? I would like to talk first of all about a single component gas. So what is this is constituted by classical relativistic particles. And let's assume that all these particles have equal properties, mass and charge. So this could be stars, it could also be dark matter particles. Just as for simplicity, let's just assume that there is only one species of particles. Then these particles will follow geodesic curves unless they interact with each other. If they have any interactions with other particles, they will somehow bounce in some way. But between those, let's assume that they are just following the geodesics of space-time. But what exactly these geodesics will be, well, depends, of course, on the gravity model, but this I will come to in a moment. Now, there is a special case where we do not have any interactions, and in this case, the particles just follow geodesics throughout. And this I will mostly assume during this presentation. And, we could also have multi-component gas where we have multiple types of particles that can even change into each other. So we can have, for example, ionization processes and recombination processes where we make a change between charged and non-charged particles and photons that can then all be described by such different distributions. Now, a bit to the mathematical background, let me introduce the important mathematical object we use here, the so-called one-particle distribution function. And the idea here is that we can describe these kind of fluids by a density on the space of velocities, actually. So instead of giving at each point on space-time a density, pressure, and also a velocity of the gas, we assume that these particles all have their own positions and velocities, or rather 4 velocities, since we are in a relativistic setting, of course. And we just want to describe how many particles are there with a certain velocity at a certain point. So we need the space of physical velocities, and this means that these must be unit time-like future-pointing vectors that describe these particle velocities, and then we describe the density on this physical space. Now, how can we do this in a pictorial way? Assume this is basically this phase space of particle trajectories, basically. And if we have just particle trajectories in this space, then they can be more dense regions where we have more particles, or more sparse where we have less particles. And what we want to find is such a function that is described here as this red region that simply takes a larger value where we have a higher density. And this green object here symbolizes basically the shell of these future unit time-like vectors, which describe the physical velocities. And the idea here is that we can introduce this function phi as via this integral here. So we count the number of particles that pass through some hypersurface. So a codimensional one surface in this velocity space, and we simply count how many particle trajectories are passing through this hypersurface, and then we write this as an integral over some function, which is this distribution function over this hypersurface with some kind of volume element here. So this is just in order to make a well-defined integral here, where the counting of the particle trajectories here respects the orientation. So if I have, for example, a closed surface, let's say a sphere where my particles go in and out, then there is no creation or annihilation inside, then this would just be 0 in that case. Now, for multi-component fluids, if I have several particle species, I would just use one function for each component. Now, how can we describe, for example, collisions in this model? So if we have a collision in this model, then it means that here we have let's say, a point-like interaction. So I don't want to model the actual force between these particles. Let's assume that there is maybe some kind of quantum interaction or something that basically just is instantaneous and happens at one point. So at this one point in space-time here, we have incoming trajectories, we have outgoing trajectories, and the feature of a collision is that it changes the momenta of the particles, or the velocities of the particles. So while they are all meeting here at the same point in space and time, their velocities, the velocity of this particle here just suddenly changes from this value to a different value, and also the same for the second particle. So this is the space-time picture. If you look at this in the phase space picture, it just means if they meet at all the same space-time point, then they meet basically at this same slice that we see here. So this is basically how we describe a space-time point in the phase space. But the different points along this surface here are the different velocities. And so we have incoming particles with certain velocities here. Their velocity changes instantaneously, and suddenly we have outgoing particles with a different velocity. So basically here the trajectories just end at this point and start at some other point again. So it's like a discontinuous jump. That is the important picture here. While these curves here are just geodesic, so they just follow the geometry of space-time. And here, this is basically what the geodesic then looks like in the phase space. Now, that means that we can calculate something from this collision rate here. So if we know the collision rate, we can do this integral that I've just shown before. And now if I integrate here around such a collision point, basically where I have a particle that suddenly appears with this velocity, then clearly around this closed surface here, the integral will be different from 0 because I have an outgoing particle but no incoming particle. And so basically the integral over any closed surface here corresponds to the number of collisions. So the collision density basically I can describe this way. Well, I can use Stokes' theorem, and basically instead of integrating over the surface, I can integrate over the volume. And then with a bit mathematics, I find a certain equation here, and I find a certain derivative of this density function here describes the collision density. And basically, this is how I can describe then the rate of collisions. Now, in particular, what I would like to focus on most is the collisionless fluid. And in this case, these points don't occur. So that means in particular, if I have a closed surface, the integral will always be 0. And that means that also this expression here on the right-hand side must be 0. So this expression here under the integral in particular must be 0, since this holds for all volumes. And this already gives me the equation of motion for the collisionless fluid. This is called the Liouville equation, and this describes the motion of my fluid. And it's essentially, it says that along these integral curves of some certain vector field, and these integral curves are just the trajectories here in the phase space, this function phi is constant. So if I have any function phi, any distribution here, it will just be constant along these classical particle trajectories. To give you some very simple examples, let's look at the dust model, for example. For a dust model, we have at each point in space-time only one velocity, which the particles move with. And this is basically like a delta distribution here in the velocity space. Now, this is here the phase space picture where I have this density function. Now, in the picture of space-time, it just means that we have such a flow of particles that just follows certain flow lines, and which can, of course, change over time. So it's not prohibited to have a turbulent flow. The important point is that at each moment, in each point in space-time, we have just one velocity. Now, collisionless fluid, we can also have several velocities at the same time populated. So here again, I'm showing the phase space picture. So in the picture of the of space-time here, we could have, for example, two clouds of dark matter passing each other without any collision. So we have particles going in one direction, particles going in the other directions, and they just pass by. But of course, if we have an interacting medium, let's say a gas, hydrogen in particular, of course, then we might also have interactions. So these particles really collide with each other, heat up. This is what is introduced by this distribution here that gets wider. This, if you assume, for example, the Maxwell distribution, this would just get wider if we have a gas that heats up due to the collision. Now, let me not so much go into the mathematics. So basically, we have certain variables that we can use. For example, for this dust fluid, we can use the mass density and the velocity, and we can then calculate the particle density function. And well, not go too much to the equations here. Basically, what we get after some calculation using this Liouville equation that I've shown before is actually just the usual Euler equations that we get for the gas. So the Euler equations are just an example of the dynamics of such a gas where we assume simply mass density and the velocity. And well, we can, here already I've applied some generalized geometry. Let me not go too much into the geometry that I'm using here. This is just one example, so-called Finster geometry that we use for describing these effects. I will come to a slightly better model in a moment. Very briefly, let me also describe the gravitational field generated by such a gas. And here the idea is to start from the action of a single point particle. We know that we can describe this action by a certain line integral in generativity, and here I've already generalized this a bit to a different function that is essentially, you can see this as the same integral that you would use in generativity for calculating the action of a particle and calculating the geodesic equation from it. Now, if you have many particles, then each of them contributes to the total action of the system. So we just have a sum over all the point particles here, each of them with their own trajectories. And now the idea is we take a hypersurface of this starting point. So this is all in the phase space picture. And as we have seen before in this original picture, we can describe the number of particle trajectories that pass through this hypersurface here with some density function. We also take some hypersurface of endpoints, so we simply let these particles that start from this hypersurface here evolve over time, and we look at where they are after some time, and we get a second hypersurface where they are located afterwards. Now, the particle trajectories here is P, and so we have now the same as this is the same as the number of particles passing through the hypersurface at some time tau, which can of course be both the starting time 0 or the end time t, but can also be any time in between here. So we can in principle also take all the intermediate time steps in here. Well, and this means basically that if we take the whole the intermediate time steps here as well, we can also just calculate the volume here. And the volume basically is just the union of all these time slices that are traced out by these particles. Now we can slightly rewrite this integral, so we can rewrite this action here after a bit mathematics. So basically what we just do is we take this integral over the single time slice that had the number of particles, integrate this over time with our time parameter tau here, and now we see that these two integrals together here simply form a volume integral over this volume in phase space here. And this volume in phase space, well, we can calculate the so-called volume form here. Is actually something that I had on a previous slide. I haven't really explained these objects here, but well, this is just the canonical phase space volume and the density of particles. So we can directly relate the action of the gas to the distribution function, and this action then directly gives us the gravitational interaction. So we don't even need the particle trajectories anymore. We only need the density function to calculate the action of the gas and therefore its gravity. Now, let me not go too much to this part. So this is basically just the gravitational interaction that we have derived here. So just to show that we have some gravity model behind everything that describes then how this gas interacts. And it's actually for a certain geometry, for the metric geometry, it just becomes the Einstein-Hilbert action. So we can consider this as a correction to generativity, but I don't want to talk too much about this theory here in the background. And well, if we put all this together, this is a bit more calculation here, we get some gravitational field equation. The important thing I only want to mention here is that the source of this is now this density function that describes the gas. Some physical implications. We also not go too much into those. Basically, we find that that theory leaves an imprint on the geometry of space-time. So we need to go beyond the usual metric of space-time. We need to have corrections in any case. And we also find that in general, the gravitational field depends on the velocity of the observer. So if we have a gas distribution with different velocities, we will find some imprints on that. That's basically where I would like to get at. So here, just to give an example, the cosmological fluid, we get some equations. Actually, there is a solution by my colleagues, which I don't have here on this slide actually, but there is a solution that has been found by my colleagues, particularly Christian Pfeiffer and Nicoletta Voiko, have derived this for a simple vacuum model of cosmology. But let me come to the main result that I would like to present here, and that basically should also then be concluding my presentation. So here I would like to look at the black hole, and I would like, for simplicity, to look at the spherically symmetric black hole. So no rotation in this case, just for simplicity. Then we have, of course, if we look at Einstein gravity, we have the Schwarzschild black hole, which is a spherically symmetric space-time. So it's a vacuum solution of Einstein's equations of general relativity. In effect, it's the unique solution that has these properties according to the Birkhoff theorem. Now, what I would like to look at in particular here is a modification of this space-time. And the model I would like to use here is the so-called Kappa-Poincaré model, which is a particular choice of a quantum gravity model, or effective quantum gravity model to be precise. The idea here is to consider an interaction between particles and some quantum structure of space-time. So this quantum structure of space-time can be some small quantum fluctuations, like of the actual geometry of space-time. For example, like some small wormholes appearing, disappearing, black holes appearing, disappearing, and these kind of wobbles in space-time, or gravitational waves at very low length scales. Now, the interaction depends on the de Broglie wavelength or the momentum of the particle. So the more momentum the particle has, the stronger becomes the interaction with these small structures of space-time. So basically very similar to a photon passing by a gas cloud. A photon with very large wavelength, infrared photon will simply pass the gas cloud, but if you have any UV photon, it will scatter, of course, with the gas particles. Now,
Gli chiedevo che sono disponibile.
Excuse me?
L'indirizzo email che gli serve? Facoltativo. E se poi quelli mi spediscono gli inviti per GoToMeeting a vita?
Sorry, could you? I did not hear. Okay. Can you still hear and see me? Okay, not sure whether I'm still connected. Okay, everything is fine. Okay, great. So so basically what we are looking at here is this so-called Kappa-Poincaré modification. Here we have something which is basically something like a distinguished time direction, distinguished by a certain vector field. And this vector field, if we assume the static spherically symmetric space-time, we can have a time and radial components. And this modification that is introduced to the geometry depends on a certain parameter, which is in this case the Planck length. And if this Planck length we approximate to 0, then we approach the Schwarzschild black hole. Now, how can we describe this spherical system? Well, let me again just go a bit more quickly through this slide, because this is just theoretical background. So we have some symmetry generators, and we describe the dynamics of the gas in a Hamiltonian picture. So we want to have some Hamiltonian, and this Hamiltonian is a function on phase space. It depends on the position and the momenta of the particles, and this is just how we describe a classical relativistic particle in this space-time. And well, in the spherically symmetric case, we can introduce some nice coordinates. Again, let me not go too much into the details here. The basic point here is that we get a very simple Hamiltonian that depends on only 4 functions. We can even slightly change the coordinates by using conserved quantities. Here we have a system that has a high amount of symmetry, so we have lots of conserved quantities. We have the Noether symmetries from the rotation and the time translation that give us a conserved momentum, angular momentum and energy. We which we can describe by these 4 variables here. So the magnitude of angular momentum, the energy, and the direction of the angular momentum. And also the Hamiltonian itself is a conserved quantity, which is different from the energy in the relativistic picture. So we can even find 5 conserved quantities. And after using all these symmetries that we have and the Liouville equation that we have for the gas, we find that the distribution of the gas is actually described by a single function, which is completely integrated. So this is just an integration constant. How this depends on these 3 parameters here, because all these parameters here are constants of motion. And so in particular, we can just look at a single component of this gas here that has a certain fixed energy, angular momentum, and value of Hamiltonian. Hamiltonian value is nothing else than the mass of the particles in this case, by the so-called distribution dispersion relation. Now, in the kappa comparé case, we have a certain Hamiltonian. Let me just briefly explain what are the different terms here. This term here is just a term that comes from general relativity. If we had general relativity only, we would only have this term here. We have some extra corrections on top of this. We have this vector field Z that enters here, and the Planck length. If we let the Planck length go to 0, then all these contributions cancel, and we keep only this one here. Otherwise, we have some extra contributions here. So this is, as I mentioned, the space-time metric. This Z here must be a unit time-like vector field, and this L here is the Planck length. Now, on spherical symmetry, we can evaluate all of this. We have maximally 2 components for the metric that are relevant here, A and B, and we have 2 components for the vector field, C and D. And let me further specialize to particular values. So we want to look at Schwarzschild spacetime. In Schwarzschild spacetime, A and B are fixed, given by this function here from the Schwarzschild metric. And let's assume that this C here has this value 1 over this, and the D is 0, because then we just have this pointing in the T direction, just again for simplicity. Now let's come to the concrete results. Let's look at 2 particular examples. First, orbiting particles at a fixed angular momentum larger than 0. So the motion has some angular component, and choose the energy such that these particles are gravitationally bound. It follows that the orbit oscillates between 2 radii, and we can then calculate the number of trajectories through each time slice which have a certain value of the radial coordinate. And this is what it looks like. So to be precise here, I plotted the inverse density of particles normalized. So that means at these turning points, which I have chosen to be just 3 times and 6 times the Schwarzschild radius for simplicity, the radial density actually becomes infinite. Well, the reason for this is simply that if the particles orbit, they approach this turning point here at lower and lower velocity, and then they turn around. And simply because the velocity tends to 0 here around the turning point, it means that the density of particles in a radial slice tends to infinity. Of course, the number of particles itself is still finite. It's just the density that becomes, or the radial density that becomes infinite, and that's why it's useful to plot the inverse instead, which then goes to 0. And we see here this modification is of such a form that if we increase the control parameter, which is here the Planck length, so we start from 0 Planck length and we go to some finite value, then we see that this function here increases in this region and decreases in this region. This is the inverse density, so it means that the density actually increases near the black hole and decreases far away from it. So the density of the shape of this gas cloud changes. It becomes more dense closer to the black hole and less dense further away from the black hole. Here also you see the relative correction with respect to the Schwarzschild case. So here we see this quantum effect again in this particular case. decreasing this function here, so increasing the density and doing here the opposite. So this shifts the particles inward. Very briefly, the second example, here we assume zero angular momentum, so we assume purely radial motion. We drop the particles from infinity at zero energy, and in this case, we assume a constant flow rate through each radial slice, so we just drop at a constant rate these particles, and what we get, again, we calculate this density here, and we see in this case that the density decreases as we go from the classical limit towards the quantum correction with the finite Planck constant. So what does this mean? At constant flow rate, we have a lower density. This simply means that the velocity of the particles near the black hole is higher due to this quantum gravity effect than it would be in the classical spacetime. Okay, let me summarize. So I've looked here at kinetic gas dynamics, modeling the particle dynamics by individual point path trajectories, and then deriving this Liouville equation here for the collisionless gas. And we can actually calculate the gravity from this model, and we can couple it to our gravity theory. In cosmology, we find well, quite complicated equations, so I haven't really discussed those a lot. But the most important thing here is that we can describe this effective quantum gravity phenomenology. And even though the fundamental theory is unknown, we can still have some effective model and find observable effects from this. In particular, here, the Kappa-Poincare modification, we could see some effects near a black hole. Now, of course, some outlook. We could look at more general examples, consider spinning black holes as well, calculate these. But of course, the most interesting thing is, can we get the actual physical effects? Can we get to model systems that we can actually observe? So, for example, where we had in the first talk, we had the blazars mentioned. Actually, accretion disks and jets would be, of course, the thing that we want to model with this, or also things like tidal disruption events or the stellar wake of a passing black hole and through the galactic disk, for example, to get the actual properties. I mean, the spectra of quasars, AGN, and other objects. And of course, other models would be dark energy inflation that we can then calculate with this, and we would like to understand from this model also other effects, like, for example, the Rieck field limit. Can we see any other effects here as well? And we would like to connect these to each other. Okay, so these are the topics I wanted to mention. So I will stop here, and thank you for your attention.
Thank you very much. Is there any question or statement? If you consider the Planck distance going to zero, you should obtain the traditional result.
Yes, exactly.
Is that the point?
Yes, that's correct. So in the Planck limit, Planck length to zero, I get exactly the Schwarzschild solution in this case.
This I start to understand, not very much, but at least with this statement, I start to understand that if you impose the limitation of the Planck length, you cannot have a traditional description, but it's only in the limit of the Planck length going to zero that you have the traditional one. And in this sense, we have to understand much more, but it's certainly a courageous assumption. Maybe some of you, you will be here. When will you be here?
I will be in starting from the 20th of July.
In a while, you will be here, and we will be able to discuss. But I think in the meantime, we have at least, I asked a question while you were not here. In the case of the planned distance going to zero, he obtained traditional physics. And it's only when you consider the indeterminacy of the position due to quantum mechanics that something new happens. Well, we have to learn more, and in particular, I don't know if Gregory has any feedback. No. Shushan, did you hear?
Your second is correct.
Excuse me?
He will count length go to zero. And you will be all considered.
Exactly. For this, I think, is the crucial point. That without keeping the indeterminacy, this is the courageous thing. We try to consider the quantum just due to the indeterminacy principle of the particle. And it's very courageous, but we will be interested to learn more. I never thought about this, and we will have to. I'm happy that at least in this new direction, Sheng, we agree on understanding this point. But there is a lot to understand more generally. And especially to try to focus on the key difference of the quantum indeterminacy. Well, we will see you around the 20, and for the moment, send us whatever thing you think appropriate if we have the possibility to do it.
Yes. Okay, thank you.
Long way to go to well, anyway, we will discuss and think about it. Certainly stimulating. Do you have any comment? One you? It's very unusual. Tagi? Shushenko already did. Narek? Okay. Thank you again.
Okay, thank you.
We have a short communication by a few, very short, by Sigismondi. È in linea?
Sì, è in linea.
Sì, sono in linea, però non credo che funzioni. Mi sentite?
Ti sentiamo, ma non lungo 5-10 minuti. Perché fai? Cosa succede?
Non sta rispondendo.
Non
sta rispondendo.
Cosa?
Non sta rispondendo.
Conto, ci senti?
Vi sento. Forse è meglio che proiettate direttamente il video. Se ci sono delle domande...
Ok, adesso lo proietto io allora. Va bene, Costantino. 2 minuti e te lo collego. Costantino, l'unica cosa è devi disattivare il microfono, se no si sente il doppio audio. Adesso faccio partire il video.
Disattivato.
Xu-Guangqui, Galileo Galilei, and the Sun. A contribution to the Galileo Xu 7th meeting held in Pescara, by Costantino Sigismondi. Xu-Guangqi was born in 1562 and died in 1633, while Galileo Galilei was born 2 years later in 1564 and died 11 years later than Guangqi in 1642. They never met each other, but there were intermediaries, the Jesuits' fathers, and in particular Matteo Ricci, the famous scientist, Jesuit apostle of China, that became a notable man in the court of the emperor. The baptism of Xu-Guangqi occurred in 1603 after Xu read a book written by Matteo Ricci in one night, and he convinced that the Confucianism was not cancelled by the Catholicism. And after 8 days, the Jesuits baptized him, and they called him Paulus. Dr. Paulus was the name of Xu-Guangqi among them. There were the Christian name. There were 4 laws described by the Bishop Jin of Shanghai: nation, people, science, and church. 4 laws of Xu-Guangqi, and this is found in the paper of Gianni Valente, exit in 2016. Xu-Guangqi is a servant of God in the Catholic Church. When the telescope arrived in China, there are several Jesuits. Manuel Diaz the Younger, young Manuo in Chinese, in 1615, he was a Portuguese Jesuit. He wrote a book, Tian Ben Lue Explicatio Sphaerae Celestics, Explication of a Celestial Sphere, where the telescope is firstly described. This Jesuit was probably taught by Giovanni Paolo Lembo in Lisbona. He taught since 1615, then there is 2 years of difference. He taught the Jesuits going abroad to build telescopes. 1618, Johannes Terentius, he was the next member of Lincei Academy after Galileo Galilei, and he became Jesuit and religious, so he had to exit the academia, but he brought a telescope in China, the telescope that the last emperor of Ming dynasty, Chongzhen, acquired in 1634. 1626, Johann Adam Charles von Bell, Tang Rou Wang, in Chinese, published the Chinese treatise on the telescope known as the Yuan Jing Shuo, the far-seeing optic glass. Is the first drawing of a telescope available in China. These information are coming from John Needham, Science and Civilization in China, volume number 3. The link is here available in this presentation. Here the drawing of the telescope made by Charles von Bell in the book Wang Qing Shuo. Is the first news of a telescope in China. The same Terentius, the one who brought the telescope in 10 years before, describes the sunspots as observed with the telescope by Galileo in Se Tien Yuo Shuo, brief description of the measurement of heaven. The Chinese, we know, they observed the sunspots by naked eye occasionally since 12th century, but also in Europe. This in the left side, we have the representation of European observation occurred on 8th of December 1128 of the Christian era. It is described by John of Worcester in a manuscript in England. The right side image is in a Japanese manuscript, but written in Chinese, and it is an evidence of observations of this phenomenon by Chinese, even before the discovery of the telescope. This occurred in Europe, this occurred in China, but this was not enough to establish the observation of the sunspots. This is a graphic published by Vaquero et al. In 1997, showing the number of naked eye sunspots along the last 2 millennia. The peaks corresponds to more observations of sunspots, occasional sunspots, and the absence of them are between 600 and 800, and during the Spörer minimum in 1450 to 1550 about. This minimum preceded the discovery of the sunspots by Galileo Galilei with the telescope. There were instruments that would allow these observations. The meridian lines with pinhole as observed as objective, but they were not able to see anything during the Spörer minimum. The first one was in 1475 in the Dome of Florence, along 2 months around the summer solstice. An image of the sun 1 meter wide was available, and it was possible to see the sunspots, but there weren't sunspots. So Galileo had to observe this, could observe the sun like first in the history, and observing the sunspot. Here in Italian is written the drawing of the great sunspot seen with the naked eye, simple sight, in Italian, by Mr. Galilei, and finally shown to many in the days 19, 20, 21, August 1612. The last image is 21st of August 1612, here I written 21, and Galileo included also the references of naked eye observation in the history by Heynard, Vita Caroli Magni, chapter 32. At the time of Charlemagne, a sunspot was seen for 7 days. Galileo, as I said, was decisive for the discovery of sunspots. After the Spörer minimum, even Kepler observed a sunspot occasionally, but he missed to understand their solar nature. I say the fact that the sunspots were really a solar phenomenon and not an accident. This is available in the paper I submit to Histories. It's a preprint of 2025. Eclipse of 21st of June 1629 in Beijing is the eclipse after a defeat of Chinese astronomy to predict another one in 1610 to predict correctly the magnitude, not to predict the eclipse, because already in 2 millennia before Christ, two astronomers, E and Ho, were beheaded because they didn't predict an eclipse. And the emperor was the son of the heaven, and so he had to know very well astronomical phenomena. The Bureau of Astronomy was very important in China at that time. So there are many papers dealing with observation of eclipses in China at the time of Jesuits. This one permitted to the Jesuits, thanks to Xu-Guangqi, to become relevant in the Chinese astronomy and to help the office, the bureau, the astronomical bureau of the emperor. The Jesuit won 3-2 if we use a soccer score, according to Sperello, Serego, Alighieri, the author of this paper, in which Journal of Astronomy and History and Heritage of 2020, he estimates the error bars in time like 15 minutes, and the observations were made without telescope, but the Jesuits fit better the observation because they predicted an eclipse of magnitude 2 Fen, 0.2, while the Chinese and the Muslim predicted 3 Fen and 24 Miao, so 0.324. NASA, with modern knowledge of celestial mechanics, predicted 0.168. The first observation of eclipses with the telescope was made in 1631. This is mentioned in the book of Xu-Guangqi. Was originally compiled on the basis of European astronomy from 1628 to 1644, it test 11 years after the death of Xu-Guangqi and the year of the end of Ming dynasty. The error bars of the magnitude were ranging from 0.05, so it means 5 Miao, with the unaided eye, to 3 Miao, when low quality telescopes were used starting from 1750. This news is taken by Yunli Shi in a paper of the year 2000. Thank you for your kind attention.
Okay, thank you.
Thank you to you.
Coffee. You have any comment?
Fascinating.
Okay, we will insert this. It's a good record. And all of Xu-Guangqi. You can go up for comment. And 45 we have to give because there is
Luciano. Luciano?
Hello?
Seems everybody is at the coffee break.
Yeah, I don't seem to be able to share my screen.
I wouldn't know how to do this either. Maybe they have to give you special permission when they come back.
Oh, okay. I'll wait then.
Because for me, the sign sharing screen is kind of dark. So it says when I go there with the mouse, I
Yeah.
should ask the organizer to allow me.
Yes. Hi there. Hi,
Yes.
Yuka. Hi, Grant. Yes, they went to the coffee break, but then when they come back, yes, they have to authorize the
Okay.
you to screen this for you to share the screen. Yes.
Okay. Very good.
Okay, Grant, start sharing your screen.
Okay. Let's see. It says I have to open preferences. And restart the browser. Is that right?
You, we can hear you.
Let's see. There's no. There it is. Okay. Let's see. Okay. Do I have to restart PowerPoint now?
You are not sharing the screen. You need to click the button to share, then entire screen, and then you can share.
Okay. I have to open preferences, unlock. It wants the browser to open up, but I'm not using the browser. Sorry. You don't see my screen, I take it.
No,
I'll open the browser, but we're not using the browser, which is why I don't understand it. But okay. And okay. I guess I have to restart PowerPoint, is what it's telling me. Yeah, okay. It'll be a second. Ah, gives me the same error again, even though the icon. Okay. Okay. I'm not sure what the problem is. I give it permission to share the PowerPoint window, but it keeps telling me I have to restart and unlock, which I've done. Okay. Are you able to see my screen now?
Yes, we can see your screen. We can hear you.
Oh, sorry about that. I had to restart the browser and PowerPoint in order to get it to work. Let me know when I should start.
Now you can start.
Okay. Well, thanks for the chance to share this talk. It's a little hobby I've been working on for a few years. And it's really to look at a simple question, whether or not it's possible that one could observe the formation of quark matter during a binary neutron star merger. Now, we've heard talks at this workshop, which I've enjoyed, including, for example, importance of MHD, which is something we're working on. But this is just a simple calculation based on the relativistic hydrodynamics, inserting the equation of state, and then seeing if we can probe the mysteries of the quark matter. There was a recent review paper on this that I like to point to. It shows pressure versus the density in units of the nuclear saturation density. And the key region we want to get into is up here. Measured neutron star masses don't get us there. Nuclear experiments only get part way. But to really see this QCD regime, one needs to look at the post-merger gravity waves and the electromagnetic signals. The in-spiral doesn't quite get us far enough, but we'll go into that. This work started as a PhD thesis work of my student Atul Kadia, which we published first paper on this a couple of years ago. And since has been taken over by my Chinese student Wei Sun. So in the spirit of Chinese collaboration, she's a very excellent student. Will be looking for a job in the not too distant future. So these are fully relativistic, based on the BSSN solution, the field equations, adaptive mesh refinement in the hydro. It's all built out of the architecture of the Einstein toolkit. So people have looked for a lot of years. This is just a shortened list of some of the many people who have written papers on the subject of the formation of quark matter during the collapse. A lot of the papers consider a first order transition. Now, a first order transition would give a signal right away because if you get into a first order transition, the pressure support of the star diminishes, and in fact, the collapse to a black hole is accelerated. So the signal would just go away, which doesn't really teach you much. The thing I'm more interested in is, since we don't know the order of the transition yet, at least at finite density, it might be a weakly first order or a simple crossover transition, like an ionization. Now, the reason this is interesting is because this is an old plot from 2003, but if you look at the phase diagram, there's potential for rich physics if one can explore the color, superconducting, flavor lock, KN condensation, etc., things that might go on out there. And I've roughly sketched kind of the evolution of the temperature and density in a neutron star merger that goes into this regime. So the basis of the work we've been doing, there are other QCD equations of state out there, and Wei Sun is actually working on implementing those. But what I'll talk about today is what was called the quark-hadron crossover, developed by Gordon Bain back in 2019 and revised in 2021. I'll talk about that. In 2022, treats the transition as a smooth crossover that's actually easier to implement numerically than a first order. And it treats the quark matter with the Nambu, Jonas, Lucinio, effective Lagrangian, which has, the usual Dirac-like term, a 4-body and a 6-body. If we analyze this Lagrangian a little bit, there's a pseudo-scalar term, provides constituent quark masses. There's a diquark term that provides the quark pairing and so forth. And then there's this vector term that needs to be added. Oops. I have to share my screen again somehow. I lost that. Okay, sorry about that. The vector term is a negative sign. It provides a repulsion, which is really needed to make a realistic quark matter neutron star. There are 3 coupling constants. First one's kind of fixed, and the other 2 constants you can treat as being correlated, this vector piece and the diquark pairing. So as one increases those, A, B, C, D, one in fact increases the strength of the diquark coupling. This is just a plot from the original paper showing it's subliminal. But important thing is, as one goes through this A, B, C, D, the pressure in the regime of a few times nuclear matter density increases as you increase the strength of this diquark pairing together with this vector piece, which pushes up the pressure. And that actually makes effect in the mass radius relation. Now, the thing about going to this QHC 19 figure, this is the mass radius relationship. The LIGO and the gravity wave observatories and the NICER data constrain actually narrower some range of radii for the low mass neutron stars, but for higher mass neutron stars, actually NICER has data consistent with much larger radii. Now, that would imply you need a soft crust in order to get the 1.4 solar mass radius small, but you need a large pressure in the interior, a central pressure, in order to get larger radii for the more massive stars. And that's why the QHC 21 was invented. And this shows up in this is a whole range of different equations of state I'm not going to describe, but as you go to fit the NICER data, then one requires even higher pressure in the interior in the range of a few.
Grant, N0 is nuclear saturation density? The unit?
Yes, that's the saturation density.
Okay.
It's 2.4 10 to the 13 grams per centimeter cube. Okay, so then the question is, what's the effect if you do a collapse with a purely hadronic equation of state? I'll show one with just the SLY. On the right side is with the QHC 19. And the thing to look at is the code time. They're not exactly synced, but they're the same baryon mass. The black hole forms very quickly in about 20 milliseconds for the hadronic equation state, but you see this higher pressure in the interior affects the hyperneutron star that's formed. It actually evolves for a long time before it finally forms a black hole. And then the next question is now to to be consistent with the nicer data, you need even higher pressure. So this again, it was two different calculations, but they're the same baryon mass, as identical as we could get them. On the left is the QHC-19, it's the B, so it's a relatively weak pairing term and vector term compared with the QHC-21. And the difference is really just as dramatic. So this one's going to collapse actually in about 20 milliseconds because it's a weaker form. But if you look, the new newer QHC-21 equation of state continues for a long time. In fact, we ran out. This particular run only goes to about 40 or 50 milliseconds. It still hadn't formed a black hole. Okay, I don't need to explain how we get gravity waves from the wild curvature tensor to this crowd. It is one of the dark secrets here that in order to do that, the real signal, if you just take the raw simulation, is very scattered. You need to fit it with the multipole expansion to get out the gravity waves. But this is kind of an illustration of what we see. The chirp as the stars approach each other, then they briefly sphericalize, which you could briefly see in that simulation. And then they go into this extended ring down. The last slide I showed this QHC-19b simulation that collapsed fairly quickly. And this is, let's see, this is going to the QHC-21, and you see there's this extended high frequency emission from that hyperneutron star. If you look at the spectrum, what the original LIGO binary neutron star sort of ended on this version, and what we're looking for is this high frequency enduring ringing hyperneutron star as the signal of evidence of the crossover to quark matter. Of course, in the real world, one has to analyze this with the Fourier modes and construct a thing called the power spectral density, which is basically the amount of power in different frequency bands. The in-spiral would show up here. The LIGO detection was around 700 hertz. But this effect of this quark matter would show up as this high frequency 3 kilohertz enhanced power. Notice the QHC-19, for example, has a much stronger peak here. We call this F peak. Some people call it F2. Whereas the normal hadronic equations of state don't show evidence of enhanced ringing up here. Maybe for a stiff one, there's a little bit at lower frequency. Now, what happened? When we went to, I did want to point out, the advanced LIGO couldn't see this ringing, but the Einstein telescope and the Compton Explorer, if the sensitivity reaches the predicted value, should be able to see this. Okay, when we go to the 21 equation of state, just want to point this out, the frequency gets a little bit lower, but the strength of this 3 kilohertz power and the power spectral density is very striking and should be easy to see. Okay, and then in the end, there are lots of papers about this. How would you detect that, recognize that in a given event if you can see this high frequency hyperneutron star? People talk about universality relations. This happens to be one. It's that 3 kilohertz peak versus sort of an average density. You could also make it against the tidal polarizability, or you can make one peak against another. There's a second peak that relates to the shift in the phase, the maximum of that. Anyway, what we think is that in a other people have pointed out things like this, you would get outliers in what might be a universality relation or a hadronic equation state between the frequency of this peak and some other variable, for example, average density. Okay, that sort of takes you through the whirlwind of what I wanted to talk about. Let me just summarize my conclusion. If there's a first order transition, it'd be hard to learn much from it other than that it existed. But a crossover transition could give an opportunity to use the gravity waves to explore the regime of this non-perturbative quark matter. Now, clearly, a more complicated simulation needs to be done that includes the MHT. And by the way, we had minimal neutrino transport in this, which affects it as well. But this simulation seems to suggest that in the next generation of gravity wave detectors, one might see evidence of this 3 kilohertz delayed post-merger peak that endures for hundreds of milliseconds even. And in fact, from the strength of that peak, roughly one can read off what is the strength of that diquark pairing, and if this QHC type equation state, the NJL model is right, and then one might detect it as outliers in various universality relations between FPAC, this peak frequency, other frequencies, or other variables. And with that, I'll stop. Thanks.
Very interesting. However, I sent you a paper which we just submitted yesterday.
Yeah.
We managed to reconsider a short GRP 090510.
Yeah.
We already published a paper 10 years ago, because at that time we were still under the idea developed with Wilson, that the charge could mimic the electric field to create vacuum polarization and therefore the Maverick emission.
Yeah.
Now we have changed. We have been able to consider, instead of binary neutron star, binary neutron star with a magnetic field.
Yeah.
A magnetic field.
Yeah. Yeah.
And what is very remarkable is, as you recall maybe, we have defined with Rueda a relation between the effective charge and the J of a rotating object and the magnetic field.
Yeah. I saw that in the paper.
A rotating neutron star, can you hear me? You hear me? Yes?
Yes, I hear you.
A rotating neutron star will have a J, and a magnetic field will have a charge. Now, in imposing the same condition for the binary neutron star we had started, we can make that application and solve for the magnetic field in that solution. But moreover, thanks to the fact that we now we have an upper limit on the neutron star limit by the experiment, by the observation of this guy at Stanford, which is 2.3 solar masses, we could determine extremely accurate the mass of the black hole. Extremely accurately. But this means that all the consideration based on the way Thibault did the work on zero magnetic field is nonsense, because the electromagnetic field coming up is larger than the gravitational wave. And the fact that they have confirmed the result of Thibault is just absurd, because you cannot have a neutron star without magnetic field. It would be with zero magnetic field. It's just impossible. Therefore, you will read this paper, and I would like to have your feedback as soon as possible.
I think it's the paper that I saw and read. It's good work. I like it. And yes, magnetic fields are important. In fact, Wei Sun, my student, is working even as we speak on implementing MHD into our simulations. So, yes.
The other thing, it's impossible that these people saw this gravitational wave. I mean, it's nonsense. But anyway, let me tell you another thing that we understand. I think the general GRB has two supernova, not one.
Yes, you made that point. That's very interesting.
First supernova is a pair supernova, very powerful, which is followed after 5, 6, 7 seconds, depend, by the other supernova, which is the core collapse supernova. Both of them. Both of them. Now, in the paper that I just sent to you, be careful, because there is a mechanism of jet. New. And we are developing that appendix for explaining the jet. Please look at that carefully.
Okay, I'll look through that. Thanks, Ramo.
For the very interesting talk. Bye. There are other questions? There are other questions? Excuse me? Last question. Okay. Okay. Done.
Thanks, Ramo.
May I ask a question?
That's okay.
Yes, of course.
Maybe they don't hear me.
I hear you.
It's okay.
I hear you.
Okay. They don't know that I am asking, so they will cut probably.
No, wait a second. Yes, who was speaking?
Yes, it's Jorge. Jorge speaking. I want to ask something to Grant, if I can.
Yes, of course.
In these simulations, I don't understand something, and it's the way once these conditions for quark transitions, or for quark deconfinement are achieved, how they progress inside the star, because they are achieved first in the center. So, I mean, the way it is treated is some a sort of deconfinement wave through the star. I was thinking that it would last more than those milliseconds time scale you were speaking about. So it's not clear to me how this process goes, because also the difference in energy between the original hadronic star and quark star are huge. So this process releases a lot of energy. How this is being accounted for in these simulations?
Yeah, the way it's implemented in these crossover equations of state is a little bit of a dark art. It's not explicitly treating here's some quark matter or here's some semi-ionization state. It's just a pressure versus density, which is really, they rely on a polynomial fit that goes from the hadronic regime, where we know, and it goes to the perturbative QCD regime that we know, and demands that the derivatives are continuous and monotonic. So it's really just a way of smoothly treating the pressure versus density plot. Does that answer your question?
So, so it's like you are assuming like that the transition is instantaneous in your simulation. Is instantaneous?
No.
This is your assumption.
Let's see. It's not an instant formation of quark gluon plasma, if that's your question. There's some fraction of quark deconfinement, if you like, that occurs that increases as you go to higher and higher density or higher and higher temperature in a crossover. It's like an ionization, but this is not explicitly treated. It's only implicitly treated in the NJL model in this version of the crossover. It's just a continuous transition that asymptotically approaches the perturbative regime.
Okay, now I understood. I understood.
Yeah.
I understood now. Thank you.
Yeah.
No, break for lunch. Thank you very much, and please read the paper today I sent to you, because we would like very much to come back with you about this double supernova, the pair supernova followed by a core collapse supernova.
Okay, I'll take a look at it.